Hi, everybody.
Talking about what's up in the sky.
What's up in the sky, yeah.
Marvelous. So, without further ado, I'd like to introduce Andy, who is from Liverpool John Moores University, and he's also director of the National Schools Observatory. And he will be talking to us about, I think, something about time domain astronomy. You're muted, by the way, Andy.
Yes. Exploring the ever-changing universe.
Exploring the ever-changing universe. So let's see if we can get the screen share working.
I will get that going right now. Well, I'll try and get that going right now. It worked a minute ago.
Love Zoom.
There we go. Are we in?
We're in.
Excellent. Thank you very much for the introduction. Shall I get going? So welcome, everybody. Thank you for joining us. I've been really looking forward to this. I've always spent a lot of my time traveling around the country talking to people, and even though I can't travel around the country, it's nice to talk to people and get some of your reactions. There is an ulterior motive a little bit to this talk, though. I have a shameless plug for a new book. It's very shiny. It's got a slightly over-the-top title of Everything You Ever Wanted to Know About the Universe. We may have overdone that a little bit. But this is my first book. I'm quite pleased with it. It's also the first book of Liverpool John Moores University Press. It may be the only book of Liverpool John Moores University Press, but at least we've got one out there. And it's a fairly broad introduction to everything that you might want to know about astronomy. So I suspect quite a few people in this session already know most of the stuff in this book. But if you have friends, family, relatives, strangers who you want to give books to, this might be a good one. So I just wanted to put that plug right up there. And this session is the formal launch of this book. It's been available to buy for a while now, but it is now officially launched as of this moment. So thank you all very much. But you're not really here for me to talk about a book. You're here for me to talk about the universe. So I'm going to be doing a little bit of exploration of how we're trying to understand what is happening out in the universe, how we're trying to make sense of it, and the technology that we need to do that properly. And I'll be talking quite a lot about this thing that you can see opening in front of you here, which is the Liverpool Telescope, which is the big toy I get to play with to try and understand all of this sort of stuff. But I'm going to start in a slightly bizarre way by telling you what astronomy is, which may seem a bit odd because you all already know what astronomy is. But astronomy does actually mean quite different things to different people. For some people, it's about looking up at the night sky, recognizing the constellations, planet spotting, looking at all the gorgeous nebulae like this one in front of you. And that's an important aspect of astronomy. It's not one that got me interested in the first place. I am basically a physicist who drifted into astronomy. So I'm interested in astronomy because it's a way of learning new physics, learning new things about the universe as a whole and the fundamental laws that govern it. And you're only going to do that if you push pretty hard. All the easy physics we've kind of done, things moving around on trolleys. We did that a while ago. Newton sorted that one out. So if we want to learn more new physics, we have to push. We have to go to the extremes, the fundamental stuff that we haven't been able to do before. And that means building experiments or doing measurements which push beyond the limits of anything we've ever been able to do before. Now, one way of doing that is building very big experiments. The Large Hadron Collider at CERN is a very good example. That thing is enormous. It's got instruments on it, sort of the equivalent of cameras the size of cathedrals. I mean, it's a vast thing. And that's one way of getting to an extremes, and it's a very good way of getting to extremes. But the other way is just finding somewhere where the extremes already exist, which is where the universe comes in. The universe is full of extreme things. And of course, it's about as fundamental as you get. It's got everything in it. I mean, a good example of an extreme thing is actually this picture in the background here. Some of you may recognize this as the Crab Nebula. It's the remnant of a supernova, sort of star that was seen to explode about 1600 years ago. And that explosion was pretty dramatic, and it left a lot of debris, and you can see the debris, and the colors tell us about chemistry and physics and all sorts of wonderful things. But perhaps the most extremes bit you can't even see. It's what's left in the middle, what's left of the star, the core of the star. Because during the explosion, the outer parts of the star get blown off into space. And that's what we're looking at here. But the inner part gets crushed by the explosion and by gravity until it becomes incredibly dense. So dense that it turns into a neutron star. To give you an idea of for those who haven't come across these in detail before, a piece of neutron star about the same size as a mobile phone will weigh as much as Wales. It's the country, not the animal. And that's insane. You know, we can't make things that dense on the Earth. The Welsh won't let us. So what we have to do is find them out in the universe, study them there, and explore them in that way. And that, to me, is what astronomy is. It's about doing physics experiments where the universe is your laboratory. And there's lots of advantages to that. As I say, there are these incredibly extreme things happening out there, and we can't reproduce them on the Earth. So we can do things that we can't do, even in giant experiments like the LHC. But there are challenges as well. And the biggest challenge is being able to see any of this stuff. You know, if I go out in the night on a nice, clear, moonless night in the middle of Liverpool, if I'm lucky, I can see this, a few dots and lots of orange, because of all the street lights. Fortunately, I don't live in Liverpool. I live a little bit outside, so I can get out onto the beach near me. And if I look north, I'm looking away from all of the cities and things. And then I can see a bit more. I can see a few more stars. I can see more of Orion in this case. I can see the Milky Way running across the sky. And that's pretty much as good as my eye has ever seen. You know, I've seen skies where I can see hundreds of stars and this beautiful glowing band of the Milky Way. And that's stunning. And for thousands of years, that was astronomy. But that's not the whole story. That's just what our eyes can pick up. And as soon as we were able to detect things, observe things that our eyes can't see, as soon as we were able to go beyond that with telescopes and with cameras, then we opened up a whole new view of the universe. And if you take a photograph of this part of the sky, for example, on a really dark site, this is quite an old photograph. It was taken with a film camera, but it does show you that the technology has allowed us to see a huge amount more. Not just more things, but more details of the things that we could already see. You can probably still see Orion there, but what you probably didn't notice before was the colors in the stars, the reddish color of some of the stars and the pinkish color of other ones. You've got these big red fuzzy blobs. They weren't there before. Even the Milky Way no longer looks like milk, fortunately. It looks like the large number of stars that it really is. So the technology allows us to see things that we weren't able to observe before. And if you can't see it, you certainly can't even try to understand it. So we're using the technology not just to answer questions, but to come up with better questions to ask in the first place. And that makes astronomy different from any other science in a fairly fundamental way. If I were to be a chemist or a biologist or most of the kinds of scientists, I would probably work in a laboratory. Probably wear a white coat. Haven't worn a white coat since I left school. And if you've got an experiment, the main thing is you can change it. If I'm a chemist and I want to heat something up, I could put a Bunsen burner under it and it gets hotter. It's not difficult. But we can't do that with the sun. We can't get a giant Bunsen burner under the sun and make it hotter to see what will happen. It's probably a good job, or some lunatic would do. But we can't change the universe. All we can do is observe it. And so we don't do experiments, we do observations. These are some of our students from Liverpool out in Tenerife, actually, as part of their degree, learning what it's like to really observe the night sky with telescopes, with instruments. And we've been doing that for more than 400 years now, and it's gone very well. We have learned a huge amount about the universe. We've learned a lot about our place in it, and how it formed and how it's evolving. But there are still some pretty fundamental questions that we haven't answered. This is a good example of something we don't understand as well as we'd like to. This is an asteroid. And it looks like a potato. They tend to look like potatoes. But it's a big rock in space. It's floating around. And there's a lot of things about this that we want to understand. We want to understand the details of what it's made of, because that will tell us a lot of the details of what the Earth was made of when it formed. It's changed a lot since then, because we have things like weather and volcanoes and tectonics and all that sort of weird stuff. Asteroids don't have any of that. They've just sat there being asteroids pretty much since they were formed. And so if we can understand them in detail, which is why missions are being sent to get bits and bring them back if they can close the doors, bringing that stuff back is important, because it helps us understand not just the asteroids, but the origin of the solar system and the origins of the Earth. Another reason why they're interesting, and this is something that I'm personally quite keen on learning more about, is they're big rocks and they're moving really fast, which means if they hit us, it's not a good thing. This would be bad news. Even by 2020 standards, this would not be good. So working out whether these things are likely to and what we might be able to do to stop that is also important. And then there's things like this, extrasolar planets. This is an artist's impression of an extrasolar planet and what it might look like from one of its moons. And the reason I'm showing you an artist's impression is because the photographs are rubbish. If you're really, really lucky, you can just about make out a small dot next to a star. Most exoplanets, we can't even do that because they're small, they're faint, they're far away, and they're next to big, bright things that we call stars. So they're very hard to study. We can detect them. We found thousands of these things, which is fantastic. But there's very few we actually know anything about other than estimates of their size, maybe density. That's it. We don't know what they're made of. We don't know what atmospheres they have. We certainly don't know if there's anything living on them. And they're questions that we would really like to know the answers to. Something else we don't properly understand, this picture I showed you before, the supernova remnant. And I talked about the neutron star that's left in the center, but actually the remnant of the explosion itself is interesting, these colored clouds, because they contain lots of different elements, more elements than existed before the star exploded. And for the heaviest elements in the universe, this is one of the most common ways they're made. And we're made of this stuff, you know, iron, zinc, all of these sort of heavier metals that is part of us, part of the world around us. They wouldn't exist without these exploding stars. But we don't understand all the details of how that happens. We don't understand all of the nuclear physics of how an exploding star makes the right amount of the right kinds of things. And it would be nice to understand that, because otherwise we don't know where the atoms in our body came from, which is not just weird, but actually, frankly, embarrassing. So we want to understand these things better. And then there's one of my personal favorites, not just ordinary black holes, but supermassive black holes. This is a particularly awesome observation, or set of observations, of the movement of stars right in the center of our own galaxy. And if you watch one of these stars, the one at the top here, you can see it going round over the course of a number of years in a perfect orbit. It's beautiful. And we understand orbits, so we can work out what's going on here. We can work out what this thing is orbiting around, and it's orbiting around something underneath that cross in the middle of the picture. And not just that, but we can work out some things about whatever's underneath that cross. We know we can't see it. There's no picture of it, so it must be dark. And we also can work out how much mass there is there. And somewhere underneath that cross is something which weighs about 3 million times as much as the sun, 3 million solar masses. And it's small because the star didn't hit it, and it's dark. So it's a black hole. It can't really be anything else. If it's not a black hole, it has to be weirder than a black hole. And we found this thing was found in the center of our own galaxy about 15 years ago, and we're finding them everywhere. Every galaxy we look at hard enough where we would expect to be able to find something like this, we always do. There are supermassive black holes in the middle, probably, of every single galaxy out there. And we don't really understand how they got there. We don't understand how they get that big. They may even turn out to be quite important to the evolution of the galaxies. You know, it seems that there's a relationship between the mass of the black hole and the number of stars in a galaxy. The bigger the black hole, the more stars. And that's partly expected, but it's very tight. It's a very neat relationship, and that's difficult to explain. So there are some unanswered questions here, which may relate to whether or not the sun would have formed without this. So maybe we only exist because this does. We don't know. Important questions. So these are 4 pretty randomly chosen bits of the universe where there are fundamental questions we haven't answered. And the main reason we haven't answered them is because they all involve changes. For the 400 odd years that we've been using telescopes, there's been a tendency to look at something and say, oh yeah, understand that, and move on. And for a lot of time, that's fine. But for these, that doesn't work. For these, you have to see how they change, either over long periods, like the supermassive black holes, or suddenly, unpredictably, like an exploding star. And that's really hard to do. But it is important, not just to understand these things, but to understand even stuff that we previously thought we did understand. This, for example, is a movie of the sun. It's a movie taken by the SOHO satellite quite a few years ago now, but I particularly like this one. And it's not the sun as we're used to seeing it. This is the sun in X-rays. Now, to make X-rays, you have to be hot. Normal light, the stuff our eyes can see, is made by things that are a few thousand degrees centigrade. The glowing stuff here you see is a couple of million degrees centigrade. And it's not an even glow. It's got shapes, it's got patterns, it's got structures. It keeps changing. There are sudden explosions, and you see those little speckles all over the camera there. That's actually particles from the sun flying out from an explosion and hitting the camera. So there's a huge amount going on. And this can affect us. For many, many thousands of years, the only real effect for this on humans was you get really nice northern lights every so often, which is great. But now we don't just have a nice, simple world where we go around, hunting for our food. We have electronics, we have satellites, we have all sorts of things which we now rely on. And this can affect them. A really big flare pointing straight towards the Earth will bathe the entire Earth in a giant electric current. And that will change the orbits of satellites. Some of them might even fall out of the sky. It will affect mobile phone signals. It will break GPS completely. GPS is not designed to cope with the sun, which I find slightly bizarre. So there's all these things that we need to be concerned about. And we can't stop the sun doing this, but if we can understand how it does it and why it does it, and most importantly, when it will do it, we can predict when the sun might have a really big flare pointing towards us. And if we can predict it, we can stop some of the damage. We can't stop it happening, but we might be able to do something about the mobile phones and GPS and power grids and all these things that can be affected. So it's something that we need to keep an eye on, something we need to understand better. And it's an important change right next door to us. Now, sometimes you see other changes. This, for example, is a change on the sun. Quite proud of that one. This is a movie that I took a few years ago. And I was trying to observe the transit of Mercury, which you can probably see as that little speck there. But after 4 or 5 hours of watching Mercury, I got a bit bored. And I was about to pack up when suddenly this plane went across. Now, okay, there's not a huge amount of physics in that, but it wasn't planned. It was a surprise. It was an accident, if you like. And importantly, I didn't get this because I was particularly clever. I got it because I was lucky. And I happened to be looking in the right place at the right time. I couldn't have predicted that. It's a Ryanair flight. Perhaps more to the point, if I'd been, 100 meters either way, I wouldn't have seen it. The angle would have been wrong. So videos like this, except when they're done by really clever people who work out flight patterns and so on in advance, you've got to be lucky. And the same is true of a lot of the discoveries in the universe. A lot of the things we've discovered have been discovered essentially, people say, by accident. But it's not really an accident as in a complete surprise. It's usually because somebody has found a new way of looking at the universe. They're looking in a way nobody's ever done before. In a sense, everything that Galileo discovered with his telescope was accidental. But he discovered it because he was the first person to take this telescope and train it at the skies and look in a systematic way at things. He found a new way of looking. And that's what dynamic astronomy, or time domain astrophysics, as Stephen called it, is. It's finding that new way of looking at the universe by looking at how things change. We know everything is changing out there. Some things change really slowly. If you go and look at Andromeda tonight, and you go back in 1,000 years and take another look, it's not going to be that different. But some things change really quickly, or unpredictably, or over timescales of hours or days or months or years. And they're very hard to study, not fundamentally, but because of the way telescopes are designed to be used. If I want to use a big telescope, say the Keck's in Hawaii or something like that, then I have to apply for time. So I write an application, many pages of waffle, frankly. That goes off to a committee who read many, many, many pages of waffle. And they go through these and they try and work out what is the most interesting things, the most productive things that the telescope can do. And if you're lucky, you get awarded time. Typically, it's about a 1 in 10 chance. And if you get your time, then under normal circumstances, you travel to where the telescope is and you go to the top of the mountain and you spend your 2 or 3 nights there at the telescope collecting your data, and you bring it back and you analyze it. And that's a wonderful way of doing science if what you're doing is going to sit and wait for you to arrive. But you can't study exploding stars like that because you don't know when they're going to explode. You can't study active galaxies like that because their timescale for variation is months to years. So there's all these things we were missing out, not because we couldn't, but because we hadn't found the right way of studying them. And the way to do this is robotic telescopes. These are telescopes specifically designed to look at these changes. And this is still the largest one in the world, the Liverpool telescope, not in Liverpool. I do a lot of work with schools, and I have to stress this point. Liverpool is not a good place to put telescopes. I was doing a the workshop with a school a few years ago in Manchester, actually. And I was talking about, why you wouldn't put a telescope in Liverpool, and I asked them for some ideas, and there were lots of great ideas. The weather's not very good, and there's lots of light pollution. And then one kid put his hand up and said, if it was in Liverpool, somebody would nick it. This is La Palma in the Canary Islands. And that thing there with the car in front of it, which is a full-size car, not a toy, is the Liverpool telescope. And inside the dome, you have this. You can see a person standing at the bottom there, my former boss, and it gives you a sense of the scale. There are much larger telescopes, but this is the largest robotic telescope, and that word robotic is what makes this telescope special. For those of you who don't know La Palma, this is it. You can see the same picture behind me. And you've got loads of telescopes up on this ridge here. There's a few more around the corner that you can't see, including the world's largest optical telescope, Grand Tecan. That little lump there is the Liverpool telescope. And it's an extraordinarily good place to put telescopes. This rocky feature that you can see is actually an eroded, extinct volcano. So you're right on the top of this ridge, and it's incredibly steep all the way around you. So basically, the weather goes round rather than over the mountain. And so it's clear 250, 300 nights a year, which is very, very good indeed. This is astronomical definitions of clear, by the way. I checked, and by that definition in Liverpool last year, there were 6 nights. So it really is an incredibly different sort of place. It's very dry, very stable. You get incredibly good views of the sky. And that's why it's covered in telescopes. It's one of the best places in the world to put them. But the Liverpool telescope is the only robotic one. All the other ones, you essentially need to be there to operate them, which does mean that most of them have been shut down for most of this year. The Liverpool telescope is different. When you're awarded time on this telescope, you don't go there. You write a computer description, basically, of what you want the telescope to be able to do. We call them observing programs. And they're collected over the internet at the Telescope Management Centre, which is basically an office in a building in Liverpool. It's a computer. That then collates them all, sends them out to La Palma over the internet, and then every night the telescope opens up and we go to bed. Nobody is in control of this telescope. It's doing it entirely on its own. So while we're asleep or at the pub or whatever else we're allowed to do this week, the telescope goes through this long list of all the things that it could do. It might be monitoring a star. It might be waiting for a star to explode and then reacting suddenly. And minute to minute, it decides what is the best thing to do next. And then it does it. And when it's done that one, it decides what's the best thing to do next. If something really exciting happens, it interrupts what it's doing and starts observing it. It's collecting information from other telescopes and from satellites. It's got its own weather station so that it can monitor the weather. It's got it actually analyzes its own data as it comes in case anything weird is happening there. So all the time it's trying to do the best possible science it can. We then get up the next day, we download the results, analyze them, and do the science. So it's a new way of doing astronomy. It's a very efficient way of doing astronomy. The telescope can work for 10, 15, 20 different astronomers every night. But the most important thing is it can look at those changes in a systematic way. You can monitor something every night. You can monitor it every night, but if it goes above a certain brightness, start looking at it every hour. You can react to sudden changes. So this means it can do science in a way that pretty much no other telescope can. That makes it popular. Lots of people want to play with this toy, and I can't blame them. Lots of people get to as well, which is nice. Astronomers at John Moores, where I work, we get a lot of time on the telescope, and we own it. That seems fair. Astronomers in Spain get quite a lot of time. La Palma is a Spanish island, and this essentially means we don't have to pay any rent, which is fine by us. But any astronomer in the world can apply for time on this telescope. And I do mean any astronomer, by the way, not any professional astronomer. You don't have to be paid to be allowed to use this telescope, basically. If you've got a good idea, then apply for time. There's even a special allocation for this. And we have had a number of nominally amateur astronomers, so people who are doing it in their own time rather than being paid to do it, who've come up with really good ideas, and the telescope has done them, and they've done the science, and it's been published. So if you have an idea, talk to somebody, talk to me, and we'll see if it will fit in with what the telescope is built to do. But right from the beginning, we also decided that just doing research was important, but wasn't the only thing the telescope could do. Because you don't have to be there, or indeed conscious, the telescope can do observations for lots of different people. And so right from the beginning, schools have been involved. This is what got me involved in the project 22 years ago now. It was to help set up what has become the National Schools Observatory, but also our students get involved. We have distance learning courses, short distance learning courses, and a master's course as well. We have our degree programs. And the students on all of these courses get to use the telescope because it brings real data to them so that they can learn how to do the science. It's a really exciting way of doing things, and I think one of the best parts of my job. In case you were wondering how on earth a school can use a £5 million robotic telescope, it's actually surprisingly easy. This is what I spent about 2 years of my life working on, so it better be easy. The idea is we have a website that guides the students, the children, through this process. They come onto the website and it helps them choose what they want to observe. And the more experience they get, the more choices they get. That then gets sent to us. This is the Telescope Management Centre, our building in Liverpool, where I haven't been since March, but it's still there. We then send those out to the telescope along with all the other requests. The telescope doesn't care whether this was an 8-year-old child or a 48-year-old professional astronomer. It will do the observations at the best possible time for that person. They then come back, we send them back to the schools, and they do this. And this can be done anywhere by anyone. It's free to all UK and Irish schools, but we've recently set it up so that anybody in the world can sign up to the Schools Observatory. Only UK and Irish schools get the full choice of observations because we've got a limited amount of telescope time. But if you want to have a play, see what the telescope can do, or you've got people who are interested in a bit of astronomy but don't like the idea of being outside at night when it's cold, this might be a good way to get them involved. So do point them at the website. So what we're doing essentially is trying to make this as similar as possible to professional observing, but removing all the really scary stuff. You can't damage the telescope. You can't damage the camera. It won't point at something that doesn't exist, that kind of thing. So certainly for the simpler options, you're guaranteed to get a result back that at least makes sense, even if it isn't quite what you expected. That's worked very well. I've got some numbers a bit later on the number of people doing this. But we can also take pretty pictures. This is an observation I took actually with our old camera many years ago for a student called Bryn Davis, one of our distance learning students, who wanted to look at star formation. He wanted to look at how stars form. And so this is a star forming region, and it looks nice, but there's also science here. The red color tells us there's a lot of hydrogen. Hydrogen glows that shade of red under the right circumstances. But you've got the dark parts, which are molecular. They're not just atoms, they're clouds of dust, and they block the light coming out from the star in the center. The star in the center is incredibly hot. It's in quite an early stage of its life, and it's still hot enough to produce a lot of ultraviolet light. And that ultraviolet light is basically boiling away the hydrogen. So this is no longer a cloud, this is a bubble. And you can see the bubble beginning to break out towards the bottom of the picture there. So there's all sorts of exciting things going on here, and it looks nice. And I actually think that's quite important. Some of my colleagues are less keen on the aesthetic side of astronomy. They're even more physicists than I am. But I think this is important because it inspires people. I did a kind of impromptu survey at a conference I was at a few years ago. And I just went around people I knew or didn't know and said, what got you interested in astronomy? And there were lots of different reasons. Some of it was television programs. Some of them had a telescope when they were little. But quite a lot of them said, I saw a really nice picture and wanted to know what it was. And that's the next step, you see. You look at the picture and say, what? You start asking questions. What, how, why? And that's what turns you into a scientist. So we do spend a certain fraction of the time on the telescope just taking nice pictures for people, because that is important. So that's a sort of introduction to the telescope. That's why we built it. And that's a description of the kind of science we want to be able to do with this, and also the kinds of education. And for the next part, I want to start going through some of the science that the telescope has done. And I'll finish off with looking into the future a little bit. And I'm going to start with just a list of some highlights. These are some of the recent science highlights from the telescope. I have a very strict definition of a highlight, by the way. I'm a scientist. I like to have a very, very well-defined criteria when I make a list of something. So with a couple of minor exceptions, these are all things where the results have been published in one of the major journals, Science or Nature. If you're lucky in your career as a scientist, you might have 1 or 2 papers in Science or Nature. They are the main journals. I think at the last count, the Liverpool Telescope had something like 30. I can't remember the exact numbers, but it's a very high number. It's a very productive telescope. And so these are ones where they're considered to be interesting to people who are not astronomers. So that's my idea of a highlight. This is some of them. We've got satellite support. I won't go through that in detail. We've got extrasolar planets. We've got novae, which are sort of smallish exploding stars. We've got supernovae, which are larger exploding stars. We've got black holes, which are made inside very large exploding stars. And we've got gamma ray bursts, which are enormous exploding stars. You might see a trend here. We do like our exploding stars. There is other science going on as well, but this is the stuff that tends to make the headlines. But alongside all of this exciting cutting edge science, we're doing work with schools. We've got over 170,000 observations requested by schools. There's been at least 4,000 schools involved, and now we've opened it up. We've got students all over the world taking observations with this telescope and doing their own science. So all of this is happening alongside the research, and we try and make sure that the school children are aware of that science, are aware of that research and how it's done by the same telescope, which I think is quite exciting for them. I think when I was in school, if I was doing my own observations alongside people who've just seen a giant star explode, I would be quite pleased. Now, I wanted to choose a couple of these to go through in a bit more detail, and I've chosen the first one, near-Earth objects, because it's a personal favorite of mine. Looking in particular at understanding the orbits of these things. Now, this is why I'm interested in near-Earth objects. Before you start panicking, this is an artist's impression. It's made up, okay? This is a drawing of what somebody believes it would have looked like when the asteroid hit the Earth that ended up wiping out the dinosaurs. Give you a sense of scale, that splash is about the same size as Germany, so it's pretty big. And as I say, about 50 million years ago, we think something like this effectively wiped out the dinosaurs. It was a complicated sequence of events, but it was triggered by something like this. That's a bit of a shame because dinosaurs are pretty cool. But selfishly, that was a good thing, because with the dinosaurs gone, we can take over. When this happened, our distant ancestors were basically large mice with weird noses. If this hadn't happened, we would probably still be large mice with weird noses, and this talk would be being given by a lizard. But it did happen. We took over and we run the world quite badly, but we now run the world. Now, we don't really want this to happen again selfishly, because if it does, we might get wiped out perhaps and something else takes over. Maybe cockroaches. They can survive anything. So unless you're a cockroach, this is a bad thing. Okay, so finding these asteroids and trying to stop them before this happens is probably a good idea. And to a certain extent, we don't need to know the details of asteroids. They're small, they're rocky, they orbit around the sun. They look like potatoes. That's probably enough to understand that the main thing we need to be aware of is, first of all, how big they are, any individual one, but also where they are. And if you look in textbooks or Wikipedia or something like that, this is the kind of diagram you will see. You'll see a sketch of the solar system with the sun in the middle, and I've drawn on the orbits of Earth and Mars and Jupiter. And between Mars and Jupiter is the asteroid belt. And it's a nice diagram. It's clean, it's simple, it's easy to understand. It's also wrong. This is not where all the asteroids are. It's where most of the asteroids are. But if instead I show you a diagram rather than a picture of where all the known asteroids were at a particular moment, I think this was about a year ago, it's a lot more complicated. There are many in the asteroid belt. They're forming that big white ring that you can see in the center. There's so many they just blur together. But there are some that are not in the asteroid belt. There are a few which follow Jupiter around. You can see a clump of them on one side and towards the bottom. They've got trapped by Jupiter's gravity, effectively. But there are also some in the middle. And these are the near-Earth objects, so called because they get near to the Earth. It's not a very imaginative name, but that's what astronomers do. Some of you may know that the largest telescope in the world is called the Very Large Telescope, officially its name, which I find embarrassing. Its successor is going to be the ELT, the Extremely Large Telescope. There was even plans for one called Owl, which I thought was an awesome name for a telescope until I discovered it stands for Overwhelmingly Large Telescope. But hey, at least they're descriptive. Now, the reason that these are of concern is they don't just get close, they can get too close. We know this happens because of things like this. This is a big hole in Arizona called the Barringer Crater, caused by a meteorite about 40,000 years ago, I believe. And it's about 1,600 meters across, about 200 meters deep, made by an asteroid that was probably about 40 meters wide, made of iron. About 1 in 10 asteroids are made of iron. You'll hear a lot more about this from Bob later, I suspect. And when it hit the ground, big explosion, made a big hole, vaporized the asteroid, and this is what you get left with. Now, 40-meter lump of iron is big, but actually, we're not too worried about these sorts of things. When they hit, they make a big hole, but unless you're underneath, that's not a major problem. And most of the time, they hit places that nobody really cares about, oceans, deserts, Manchester, things like that. So we're not that concerned about them. It's the bigger ones, 10, 100 times bigger than this, because when they hit, they don't just make a bigger hole, obviously, but they throw huge amounts of dust and ash and soot and grime into the atmosphere. And that goes to the top of the atmosphere and it spreads out until it covers the entire globe and it blocks out the sunlight. And that's what does the damage. It's not the explosion, it's the cold afterwards. I saw some calculations a while ago which showed that a big asteroid could easily make it cold enough that the entire oceans freeze over all the way to the equator. And that's not good. That's the kind of thing that can destroy civilization and possibly even species. So they're the ones we need to be aware of. And we know there's lots, but we don't know we found them all. We certainly don't know where they're all going. And so we need things like robotic telescopes, not just to find them, but to help understand whether or not we need to do something about them. The Liverpool telescope is involved in this. And it's ideal because it can do follow-up of discoveries. Smaller telescopes are very good at discovering these things, but they can't always take the detailed measurements that you need to predict an orbit accurately. So we have a simple process. One of these possible near-Earth objects, not quite sure yet, maybe, maybe not, is detected by a smaller telescope, a survey telescope, which monitors large fractions of the sky. We then estimate the orbit, schedule observations on the telescope automatically. It does those, detect the asteroid in those observations, work out a more accurate orbit. Sometimes that's enough. Sometimes you have to go back and repeat the process a couple of times. But at the end of that, we know for certain whether this thing is going to get close to the Earth, close enough to be worried about it in the next, say, 100 years, 200 years. Then you come back in 100 years and check again. 99.999% of the time, we discover that they're not dangerous, but just in case, it's that incredibly rare but incredibly dangerous one that we need to find. And this is great, but there is a slight problem. And the problem comes in the third step, detecting the asteroids in the observations. Every other part of this can be completely automated perfectly by computers. Calculating orbits, scheduling observations, all of that sort of stuff, computers can do absolutely perfectly. It's surprisingly difficult to write software which does a perfect job of detecting asteroids in observations. They tend to get confused by asteroids which are moving in slightly unusual ways, which to a certain extent is the ones we're interested in. They tend to get confused by satellites and by cosmic rays and things like that. But people are surprisingly good at this. You give somebody a set of observations and they can find the asteroid and they don't get it wrong. And they may not understand what they've seen, but they don't get it wrong. And so the best way of doing this is actually getting people to check. You use the computers as well, but you get people to check. But there's lots of asteroids and very few people. And to a certain extent, this isn't an astronomical problem. It's if you like, a health and safety issue. So we need people to do this, but there aren't lots of astronomers queuing up to help. And a few years ago, we were sitting down thinking about this problem, and we decided that what we really wanted was basically lots of people with loads of time on their hands. We call them children. So we set up a project where we take these observations and just put them on the school's observatory website. And the children, the students, come along, find the asteroid, report back. We then check those automatically and use that to refine the orbits. And basically, it takes up none of my time, but they get the fun of doing this. And I thought we'd have a quick go at doing this together. Normally do this with a group of people and I can see them all panicking, but this will do. This is an observation that contains an asteroid. First question is, can you spot it? I will give you a clue. It's not the white thing at the top. Okay. Stephen is looking very keenly at the screen. I'm cheating a little bit. This is the observation as it comes straight off the telescope. And the cameras that we put on these telescopes are much better at detecting things than our eyes are. Otherwise, we wouldn't use them. We would just look. In particular, they have a much larger dynamic range. Now, the dynamic range of something is the number of different shades of gray it can detect effectively. The eye can detect 50 different shades of gray. I used to have to explain that. But this camera can detect about 50,000 different shades of gray, which is obviously a lot more exciting. But it also means that to see what's there, we have to process the image. We have to put it into the computer and tell it what to do. So the first thing that the children do is they start doing some image processing. They'll change the the contrast a little bit, see a few more dots. Go a little bit further, see a few more dots. And you can probably see now that the sky has turned a kind of darkish grey, and you've got lots of dots on there. And now you're pretty much certain that you will be able to see everything there is to see there. Now, does anybody now think they can spot the asteroid? Just have a good look, and in your head say, I think it's that one, or I don't know. Okay. Got a few, give you a few seconds to do that. Now, some of you are probably thinking, it's just a bunch of dots. And you'd be right, it's just a bunch of dots. The problem is that asteroids look like dots because they're small, and stars look like dots because they're far away. And telling the difference is actually quite difficult. I've shown this observation to quite a few people, and a few people have guessed right. 3 people have ever known for certain which one it was, and they all do this professionally. It's not easy. So how can I expect school children to do this? We've got 6, 7-year-olds doing this. How are they going to know which one's a star and which one's not? Well, of course, we don't give them one observation, we give them several. And what you should see here is 4 observations, one after the other, and you'll see something moving in a nice straight line. And that's how you find an asteroid. You'll also see a few other things. There's a couple of little flashes. There's a little flash down in the bottom right. Every so often there's one up, sort of just up left from the center. They're cosmic rays. They're the kind of things that can confuse the software, but they're not going to confuse you because they don't go in a nice straight line. And so that's what we're doing. We've got schools all over the country doing this, in fact, all over the world now. We typically have a new set of observations of one of these things that we need to follow up every week. So if you're interested, come along to the website, have a play yourself, see what you can find. There's quite a few observations. Most of them are a lot harder than this one, but they are still there and they can still be done. So if you're interested, that's the website. So that's one example of science that the telescope is doing. But actually, it's not really science. As I said, it's more health and safety. It's important and it's fun. But I wanted to talk about one area of actual science. And the one I've chosen is exoplanets, extrasolar planets, planets going around stars other than the sun. Because everybody wants to know about these things. Everybody wants to know about the planets. They want to know about the life out there in the universe. And there are lots of different ways of trying to find these things, but one of the most successful is called transits. This is another artist's impression by Mark Garlick, and it shows what you would see as a planet passes between you and a star if you were really close to the star. Now, we don't see this from where we are, we see a dot. But of course, at the moment that the planet is there, some of the starlight isn't reaching you. And so the star will be slightly fainter than it would be when the planet isn't there. And as it goes around its orbit, the star will get fainter and brighter, fainter and brighter, fainter and brighter. And this is used to find exoplanets. But you can also use it to find systems of exoplanets. If they're all in the same plane, like they are in the solar system, then several of them might cross in front of the star at different points in their orbits. And then you start to see lots of them. And one of the most successful ones of these is a system called TRAPPIST-1, which is found by TRAPPIST collaboration, which involved quite a lot of different telescopes, including the Liverpool telescope. And they found 7 planets about the same size as the Earth going around one star. Now, when you read this in the newspaper, they talked about finding 7 Earths. This is not the case. They found 7 things which are sort of a bit like the size of the Earth-ish, which is as good as we can do nowadays. That doesn't mean that they've got, continents and oceans and America on them and things like that. But nevertheless, it is an important step forward, and it's a very exciting system. And this is the kind of data that you're getting. On the left here, you can see light curves. These are measurements of the brightness of the star. And you can see for each one, you've got a dip. And these are the dips in brightness caused by those 7 planets. And the depth of the dip tells you how big the star is. Sorry, how big the planet is. The more light it blocks, the bigger the planet, and therefore the bigger the dip. And the length tells you how slowly it's moving, because it takes longer to cross the disk of the star. And so that tells us about its orbit. And so we can work out the orbits of these planets. Now that looks pretty easy. Actually, the real data is a bit more like this. This is the kind of thing you actually have to get used to when you're dealing with these. So we're looking at the brightness of the star, and it drops, and then it drops again, and then it goes up a little bit further than it just dropped, and then it goes up again, and then it goes back to normal. And that's because there's actually 3 different planets here. 2 of them start crossing at the same time, just to be awkward. A third one joins it. then the first one leaves, the second one leaves, the third one leaves. So this is the kind of data you're dealing with. And so you've got to keep coming back again and again and again, making measurements. And the Liverpool telescope is great for this because it can fill in the gaps. When another telescope isn't going to be able to do it, it can immediately change what it's doing and start doing this just to fill in some gaps. So it's a very powerful part of the network. And these sort of collaborative network approaches are very important to the operation of the telescope. Doing things alone, there's no real future, and you've got to work together, you've got to collaborate. Which brings me to the future. This telescope has been operating successfully as a robotic telescope for 15, 16 years now, and it's done a lot of exciting science. We've been able to keep it up to date by changing the instruments, building better cameras, spectrographs, that kind of thing. But there's going to come a point where this telescope is no longer able to really do the cutting edge stuff. Typically, 10 years, you're pushing it, 15 years, you've had enough. We've already had 15 years, and I reckon another 5 or 6 years is fine. But beyond that, we're going to be able to, there's going to be other facilities that can do at least as good a job. So you need to think to the future. And so you've got to start thinking about not what are the scientific challenges now, but what will the challenges be in 5, 10 years' time? Because that's how long it's going to take to design and build the telescope. And we've been doing that process for about 5 years now. And one of the main things that people are excited about at the moment, for good reason, are gravitational waves. When I was doing my PhD more years ago than I care to remember, I did it in Glasgow. And down in the basement of the physics building in Glasgow was a group of people who were trying to measure tiny vibrations of a mirror. The level of vibration was such that although I was 6 floors above them, they could tell when I flushed the toilet. It was absolutely extraordinary. And they were part of a group that's trying to measure these tiny little fluctuations that are caused by ripples in space-time moving through space. And the main cause of these ripples is massive but very small objects smashing into each other at nearly the speed of light. The obvious example is 2 black holes spiraling in together and banging into each other. And people have been looking for these things for a long time. And like fusion energy, it was always 20 years ago, until suddenly it wasn't. Suddenly it happened. Earlier, I think, than most people expected, because they hadn't finished commissioning the instrument when they saw this. The instrument here is LIGO. LIGO at this stage came in 2 parts, one in Hanford and one in Livingston. These are huge experiments, kilometers in size, where they measure tiny movements, much, much, much less than the size of an atom of a mirror. And they use those tiny movements to work out where the gravitational waves have passed through. Now, if you saw one of these on a single instrument, you wouldn't believe it. But if you see it on 2, and it follows exactly the right shape, and the shape is exactly as you predict, you start believing it. And that's what they saw. These 2 colored traces here are detections of tiny, tiny little fluctuations over less than a second of 2 of these instruments at the same time. And the thin lines drawn through them is a prediction of what you would expect if 2 black holes smash into each other. And it fits perfectly. They had found gravitational waves. Since then, they found a lot more. This is the latest data from LIGO and the Virgo Consortium of pretty much all the known solar mass and above black holes and neutron stars. Now, some of these were found by traditional means using telescopes, X-ray telescopes, radio telescopes, optical telescopes, but telescopes. But if they've got these 2 lines joining them together, what you're looking at there is 2 objects smashing into each other to make a third. And they can only be found at the moment by these gravitational wave systems. And you will notice that particularly for the more massive objects, they're all found like this. If you look at the electromagnetic black holes, which are sort of in the middle here, who are sort of 5 to 20 times the mass of the sun, we found quite a few of those just using traditional telescopes. So we didn't even know that these 20, 40, 80, 100 solar mass black holes even existed. But they must do, because we've seen them smashing into each other and making new ones. We just haven't spotted them any other way. And so understanding exactly what's going on here is incredibly important. But it's difficult, because although you can detect these gravitational waves, working out where they are and following them up is quite tough. These, for example, are estimates of the position of different gravitational waves sources on the sky. So they cover, a good fraction of the entire sky. Normal telescopes don't work like that. You look at a tiny bit of the sky. And so following them up is tricky. But as they build more of these gravitational wave detectors, these weird banana shapes are going to shrink enormously. And then if you've got a good enough, fast enough telescope, you might be able to catch these things in ordinary light just after the gravitational waves have been detected. And then we can work out the physics of what is going on. So one of the motivations for a new robotic telescope is something that can do this, something that can follow up these things, which we didn't even know were going to exist when we started designing the first telescope. But there's more. Other countries are beginning to catch up with the idea that the fact that the universe changes is interesting. In particular, the Americans got excited. And when the Americans get excited, they spend a lot of money. And what they've done is they built something called the Vera Rubin Observatory, or the Vera Rubin Telescope, which should have its first light, its first sort of proper observations sometime early next year. And these are discovery telescopes. These are designed to find things that are changing. To give you an idea of what I mean by a big telescope, this is the mirror. This is the mirror before it was properly shaped for the Vera Rubin Observatory Telescope. They are real people, just to make this entirely clear. It's enormous. You'll also see it's quite thick. That's because it's designed to be very big, but have a short focal length, because then you can put a big camera on it. Now, you've all probably used digital cameras. You might have them in your mobile phone. You might even have a nice digital SLR camera or something like that. And that will have a chip in it. And if it's a really posh, expensive camera, the chip might be about this big. Mobile phones, they tend to be the size of a fingernail. This is how big the camera is going to be in the Vera Rubin Observatory. It's insane. And the idea is they will take this enormous 8-meter mirror and they will collect light in it and they will shove it on this camera and they will take pictures of most of the sky every night, night after night after night. And then huge computer systems will find anything that changes. And they're expecting to find quite a lot of things that change. They might change because they move, they might be exploding, they might be variable stars, all of these different reasons why they might change. In fact, the initial estimates I saw, and I haven't seen these change yet, is they're expecting to see about 1 million brand new objects every night for 10 years, which is fantastic. But you won't know what they all are. And but by the time they found them, it's too late for that telescope to do anything about it. Now, the vast majority, you'll be able to work out what they are. If they're moving their asteroids, if they vary in a known way, they might be Cepheid variables or something like that. Most of them will be able to work out what they are. But even if there's 1% which are weird, that's still 1,000 every night. And if it's 100%, there's still 10 every night where you don't know what's going on. And they're the ones that you need to follow up. And so what we need is a telescope which is a bit larger, because some of these things are going to be very faint, and it's got to be quicker. It's got to move fast. The current livable telescope can get from anywhere in the sky to anywhere else on the sky and start observing in about 1.5 minutes. That's too slow. We've got to get that down to about 30 seconds, which has never been done for a large telescope before. But we think it's now possible with modern techniques, modern control systems, and modern materials. And so we have a plan for these. It's codenamed the NRT, or the New Robotic Telescope. Told you we were good at names. This name will change. Don't know what it's going to change to. Probably depends on who gives us the most money, but this name will change. The idea here is the mirror will be twice the diameter, so 4 times as many photons. It's going to be light, so it will be moved very quickly. It's mainly going to have a spectrograph on it rather than a normal camera. This is essentially because the things that are discovering objects are cameras. And so to follow them up, we need something which can take detailed observations of chemistry and motion and so on. Hopefully, if we can get the full funding, we'll take the current livable telescope and remodel it as a wide field of view camera, so that it can also do follow-up and in imaging, but also find some things for itself. Design studies are nearly complete. The scientific consultations are all done. We could have first light on this as early as 2025. There's a few funding bids in, but a lot of the funding has been found. So this is going to be a really exciting thing. And alongside this, we're working with the schools. So they're going to be following the building of the telescope. They're going to be looking at the technology and the engineering and the computer science of the telescope. But they'll also be able to play with it. They're going to be able to get their own observations from this and from the remodeled livable telescope. So it's a very exciting time. Over the next 5 to 10 years, this telescope will hopefully be built and start doing science. And there's going to be an amazing range of things that we currently don't even know exist, that in 10 years' time we may even understand. It's an amazing time to be in astronomy. So summary, roughly on time as well. Excellent. Robotic telescopes are giving us a completely new way of looking at the universe. For the first time ever, we can systematically study in detail how things change, hour after hour, day after day, night after night, month after month, year after year. And the Liverpool telescope leads the way. Even after 15, 16 years, there really isn't any other telescope that can do quite the same level of detailed research in the time domain. So this is great. It's been great to be involved in it. It's been great to take part in the collaborations with other astronomers around the world. But it is just the beginning. There are so many things out there that we don't understand. There are so many things that we don't even know we don't understand yet, unknown unknowns. So it's going to get better. And this is always the case in something like astronomy. The harder you look, the more effort you put into discovering things, to understanding things, the more interesting it gets. That, I think, is the biggest joy of the job, because no matter how hard you work to answer a question, when you come up with the answer to that question, the best bit will be the better questions that you then get to play with. We're never going to run out of things to do, but we're never going to have fun doing it. So hope that's given you an idea of why I love what I do and why I find this telescope particularly exciting and interesting. If you want to know any more, here's a few websites and things like that. But in the meantime, thank you very much for listening. And I'll be delighted to answer any questions you have. Cheers.
Brilliant. Thank you very, very much. And if this were a live meeting, there'd be a huge thunderous round of applause. So we've already got some questions. Catherine on YouTube is asking, as people are talking about mining asteroids from the asteroid belt, could we test our robotic mining equipment by sending this equipment to a near-Earth object when it comes close to the Earth?
It's a good thought. That is something that people are thinking about. The problem is actually, because they're moving past the Earth, at the time they're really close, they're really hard to catch up. So they're moving quite quickly. In some ways, it's easier to send them out to the asteroid belt, because although it might take longer to get there, when you arrive, you'll be moving at basically the same speed as the asteroid, so you can slow down and park next to it relatively easily. But no, people are exploring this sort of idea. We've got a small collaboration going with a local company, actually, who are thinking of looking into how you make, if you're going to do asteroid mining, which frankly at the moment is an insane idea anyway, you're not going to make a profit doing this yet. The only way you can conceive of making a profit is if you can really target asteroids where there are things that it's worth the effort, things that are incredibly rare on the Earth, but we still need. Going out and indiscriminately mining the moon and asteroids and so on is not only an environmental catastrophe, in my opinion, but also stupid and inefficient. But if you can target a small number of asteroids which you think happen to contain large amounts of really interesting and valuable stuff, that might be sensible. But how do you know which ones? We're seeing whether you can find out using telescopes before you try and go there and chip bits off. Yeah.
We've got another question from Gerard McKentagat to the panelists. Hi, Andy. Are there any plans for a MAD day next year? I'm not sure that refers.
Oh, yes, the Merseyside Astronomy Day. Yes, we had to cancel that this year. It's normally a day of talks in Liverpool. I'm hoping to arrange one that's going to be entirely online this year. So hopefully around about March we'll be doing this, but I haven't got that finalized yet. So keep an eye out. I'm hoping to arrange that, yes. Yeah.
You've got a really good acronym there as well.
I managed to sneak that past our marketing department by only ever calling it the Merseyside Astronomy Day until the first publicity went out. But yeah.
Very good. There's another question from Paul Cass. What is the budget for the fully funded new robotic telescope?
Yeah, it's a little bit difficult to be certain on that because it depends a little bit on where you buy things from, obviously. Quite a lot of the people we're collaborating with will be providing things in kind. So, for example, it's a possibility that we'll be working with a Chinese organization that their contribution will be the mirror, for example. I'm not, that's just a random example, but it's probably going to be about 20 to 25 million euros in total, all in. All the instruments, new dome, new telescope, remodeling the Liverpool telescope and so on, which sounds like a lot of money, but actually that's pretty cheap for something that can do this much science. We're confident we'll get that. And it's going to be an international project. The Spanish are heavily involved, the Thai Thai government want to be involved, China involved, the UK are putting quite a lot in, that sort of thing. So if it all comes together at the right time, it shouldn't be a big problem to getting that amount of money together. Yeah.
And I guess it's pretty cheap on running costs because it's robotic.
It is. Yeah. I mean, I'm not sure that I'm supposed to say exact numbers, but the current running costs for the telescope is about $500,000 a year, which is and that includes instrument development and things like that. It's incredibly cheap. So yeah.
Wow.
And it's also, I mean, this wasn't part of the plan, but it's fairly pandemic proof. It turns out I think it's the only telescope on the Palmer that's kept operating right the way through the whole process, because it's designed not to have people there. So not having people there isn't a major issue. We've had to, one of the instruments has had to be shut off because it needs to be pumped and that kind of thing. But basically it's kept operating right through, which has been an unexpected benefit. Yeah.
There's a question from John Murrell. What is the magnitude limit for spectroscopy for the new robotic telescope?
That's a very good question. And I'm going to try and remember off the top of my head. We have two spectrographs. There's one called Frodo spec, which is more sensitive, but it's based on a bundle of fibers, and the data analysis is quite tricky. So that's a hard one to use, and is not. It's usually only used for quite specialist things. But there's one called Sprat. And it depends on how much time you're willing to put into it. If you spent an entire night looking at one source, you can get pretty faint. But we're typically talking, I think, about 18th, 19th magnitude for a sensible spectrum. Yeah. It's if you want to go really faint, you're not going to see how things change, frankly. You need a big telescope. But if you want to pick off things which change but we've never studied properly, this is a good one to go for.
Yeah. I guess if you're looking at, it would depend whether you're looking for faint absorption features or looking for emission lines or continuum, or
it's a medium resolution spectrograph. We're not going to be doing high resolution or anything like that. Even getting a robotic telescope was a big to do spectroscopy is a big challenge, because if you've ever, I'm sure you've done this, Stephen. If you've ever been at a big telescope doing spectroscopy, you spend a significant fraction of your time trying to get the stupid thing to sit in the middle of the slit. And you can't, doing that automatically was quite difficult. But we come up with this rather nice system, essentially where each spectrograph has a slit, an optics, and a camera. And what you can do is you can design it so that you effectively remove the optics, take a picture through the slit. Sorry, remove the slit and the optics, take a picture, put the slit back, take another picture, then put the optics in, effectively. And so you can take the initial picture, move the telescope to where you think the slit should be, take another one to check it's there, and then start taking the spectrum. That can be automated, but that took several years to get right. That's not easy. So yeah, the new one will be better at it because we've learned a lot. So the new one will be able to get really good spectra very easily.
Thank you for avoiding the temptation to use a lot of Anglo-Saxon there, because
fair enough.
Actually, I was wondering, you mentioned the Rubin Observatory, the LST. What are your views on satellite constellations?
Yes. Oh boy. It's going to be a very, very serious problem for things like the Vera Rubin. They can try and mitigate it with changing observing strategies. They can just avoid a third of the night and not bother. You can try and pick these things out in software, but when you think how big the mirror is, you don't need to have a bright satellite to pick it up. They don't have to be in sunlight. Even their own infrared glow might be enough. It's going to be a nightmare. At the moment, it looks like what it's going to do is not completely destroy the telescope, but people are only throwing ballpark figures around at the moment, but it looks like it will make it about 80% less efficient. So they're going to be doing a fifth of the science that they would otherwise have done. But that may be fixable. They may be able to find ways around that. There may be compromises that can be reached. The problem is not so much these satellites going up now. It's that there is literally no regulation of what goes into space. Nobody has any say. Anybody can launch whatever they like and do what they like with it. And that's not just a problem for astronomy. That's a major problem for anybody who needs a satellite, frankly. So I think the big push now is that this has made people aware of this issue in a way that they weren't really aware before, because there wasn't that much of a problem and it was getting a bit busy, but who cares? Now people are starting to say, no, we need to have some proper international laws on what can be launched when, why, and what the criteria are. And maybe that will have a long-term impact on these kind of things as well. Yeah.
Yeah.
But yes, it's a weird time to be doing astronomy. I've noticed, I mean, even because all the observations taken for schools, I have a look at in the morning because I'm curious, and I've started noticing more satellite trails. And that might be a coincidence. It might be because I'm spotting them, but I think actually we're starting to see them even in our tiny little observations. So
yeah, in the transfer orbits, they can be quite bright. So
absolutely, yeah.
So there was a comment from John Murrell. Actually, it looks extremely informed. Actually, thanks. The problem, as I see it, is that using Gaia as a baseline, the number of transients detected more than doubles for each magnitude. So most Vera Rubin LSST detections will be very faint.
Yes, we're I mean, the point is, when you've got 1 million new ones every night, of whom 100 are weird, realistically, you can follow up 2. So you choose the 2 you can do. There's, I mean, if we could build a sort of 40-meter rapid reaction telescope, we could still only do 2. So it's really a case of optimizing the ones you pick to make sure that you get the science, and that will evolve. Once it's been operating for 6 months or a year, some of the ones which were previously weird will start to seem normal, and we'll start looking at those and so on. So yeah, there's going to be enough bright ones that isn't an issue, but the very faint ones, you're not going to be able to follow up with the robotic observatory. They're just, it isn't feasible. There's nothing that can do that. Not for anything like a sensible budget.
Indeed. And it's also been pointed out that a problem with low Earth orbit satellites is that they're out of focus for ground-based telescopes. So you get quite a wide smeared trail.
Yes. It can be an issue, certainly. Not too bad, because they have to be, pretty low for that to be a major issue for a large telescope like this. But yeah.
Wow, I'm actually quite stunned at the technical level of these questions. Wow.
It's good, isn't it?
Yeah. There's another comment here. A very interesting talk. Thanks very much, Andy.
My pleasure. Thank you.
Yeah. I had one last question: is where will the new robotic telescope be?
Oh, right next door to the current one. We want them physically next to each other on the island, mainly for efficiency of maintenance and stuff like that, but also because put my book up again. Also because the IAC, the people who run the observatory in the Canary Islands, they're very keen and very supportive and putting up quite a lot of money. So we've got a very good working relationship with them. It's a very good observing site. Why put it anywhere else? There are slight advantages to being in the Southern Hemisphere, because that's where things like the Vera Rubin will be. But actually, there's enough overlap and so many possible objects that, again, okay, there might be, again, 50 a night, 30, 40 a night that you want to look at, of whom 10 you can't see because they're too far south. So what? It's not a big problem. So right next to the current one.
They're not too far away from the equator, these observatories.
No,
so
precisely.
There's plenty of overlap. And
there's enough sky. We don't have to worry about not having enough sky to look at. Definitely not.
Yeah. And there was a comment in the chat from Gerard McIntagat as well. Excellent book, highly recommended.
Oh, that's very nice. That's very kind of you, Gerard. Thank you. I've no idea whether it's good or not. I've read it so many times I can't make any sense of it anymore, but I'm glad people are enjoying it. Yes.
I know how it is to I mean, I've only written textbooks, but oh my god, it's hard getting it all out. And you have a really, really pretty cover, actually.
It's very shiny. Yes, the publishers Elliott and Thompson have done a splendid job on the cover and the layout and so on. I'm very pleased with it. Yeah.
Beautiful. And how do people buy it? I might as well just
all good bookshops, online retailers, and I'm not going to mention any names at all. Yes, so basically it's any way you'd normally buy a book.
Brilliant. Okay.
Yeah.
Right. Well, Christmas is coming soon, folks. So I think it's now 3:10. I think people need people have called it a P&T break or a G&T break or whatever it is. So I suggest we come back in 10 minutes for talk by Robin on what's up on the sky right now and imminently. Would that be all right, Robin?
Yeah, that's fine. Yeah, so it's now, I make it 11 minutes past 3. So if you can be back at about 20 past, then we'll start again and they can stretch their legs.
Brilliant. And thank you again, Andy. That was really, really good. I really enjoyed that.
Thank you. That was definitely my pleasure. Cheers.
Right, we'll stay online so that we haven't gone away.
Indeed. Okay, let's stop my video and stuff.
Are you there, Robin?
Yes, hi.
Hi. Before I share my screen, I'd like to show meteorites close up like this.
Oh, yeah.
So I won't start the PowerPoint until I've done that. It'll take just a few moments.
All right. Well, I'll leave you on before when we
So
come to
if
you
you
then.
can leave my full screen picture on, and then
Yep.
we can
Okay.
take it from there.
I think we're seeing a sign saying SBA back at 3:20. Another 2.5 minutes to go. Just anyone that's just tuned in knows what's going on.
Okay. Just experiment with this to see if they come out okay. Yeah, that's not too bad.
Oh, it's an iron meteorite by the look of it.
If you hold it about 10, 15 centimeters further away, it'll be slightly more in
Oh, that's
focus.
better. Yeah.
Yeah.
We get a better idea of scale. I thought it was absolutely enormous for a minute. It's just about to duck.
Get the magnet on it as well.
Oh, yes.
Lovely.
And lastly, the breccia from the Reese crater there.
Oh, nice.
Oh, yes.
It's not as big as it looks, honestly. If you put it next to my head, you can see how big it is.
Oh.
Depends how big your head is, of course.
I should start like that for a sense of scale and then move in. It's coming at you. Yeah.
Can I give my apologies if I have to leave before the end of this? I'm
Of
expecting a
course.
phone call.
It was great talk. Thank you very much. And told me lots of things I wasn't aware of about your plans for the new telescope. Absolutely fascinating.
It's so
And
exciting. Yeah.
It is.
Yeah,
yes,
very good.
yes.
Thank you.
Yes, the fact that we're live will show people that there is something to look forward to, and we're coming back again. While I'm screen sharing, I can't look back at the number of participants. I'm pleased to see there are a few people I haven't seen at a meeting for a while, and it's nice to see you online. I noticed Paul Cass. Hello, if you're watching, Paul, a very long-term member. And Barbara Kern, also I noticed there. Nice to see you, old friends of mine. Shame I can't see you in person. Paul Cass was an early editor of our magazine. At least he was meant to be. And he agreed to do the job. This is back in the 70s. And then got very busy. And so Paul Sutherland said he would help out for an issue or two. And well, Paul Cass never managed to get back to the job. But I'm glad to say he's still a member. And nice to see him attending the meeting. And you can put messages into chat. Anyone who's watching the YouTube channel, no, we haven't got any more strange messages there. There were some curious ones from some gentleman who kept on reappearing under different names. And if he's watching, well, I'm pretty sure that Comic Atlas isn't going to hit the Earth. It's well on its way away from the sun at the moment, and so fragments of it are not going to hit the Earth, and that's not the reason for lockdown, I'm pretty sure. So I had to delete those messages, but I think we have to stick to mainstream astronomy on this channel.
It's one of those rare things that people. Well, I'd say it's very easy to underestimate just how gigantic the edifice of evidence is in sciences. And so, I mean, all academics, honestly, we are at heart contrarians. We are all looking for the idea that nobody else has spotted, and that angle that no one else has got. But it's really hard, and that's why it all seems like we're all towing the same line, is because there's just a lot of evidence.
Yes. And I see Paul says in the chat that yes, Paul Sutherland, I got lumbered. That's what he said. But he did a very good job. Sorry, I'm just running over my microphone cable, which is not a good idea. He got one of those wheelie chairs and usually managed to run over something. Yes, Madeline Dunn says, I've never attended meetings in London, so it's quite nice to Zoom. Yes, nice to hear from you as well.
And this is one positive development, I would say, is that people connect in a way online that has just not been possible before. And I do like that. There are lots of things I don't like, but about the current turmoil, but I do like that very much.
I noticed there's a Q&A from Roy Groom, and this is one for Andy, which might as well cover since waiting for people to return. If it's not too late, when building a new telescope, this is on the one you're planning to build, does it disturb the others nearby? Which is a very good point, isn't it?
In principle, but in practice, you work very, very hard not to. So yeah, there's a lot of, you need to make sure you don't kick up any dust. You need to make sure that you only work during the hours of daylight, all these sorts of things. It's usually pretty, they've got the techniques down pat. We have the advantage that we're probably going to be taking over a site which has an old telescope, an old defunct telescope on it. So that will be a little bit less churning around that needs doing and groundworks and so on. But yeah, the main problem is making sure you don't kick up dust, and they work very hard to do that. Yeah.
So which telescope? You're binning the WHT, yeah?
Oh yeah, get rid of that. Do you know, I can't remember. It's just round the corner up a bit. It might be the old Carlsberg Meridian, but I could be wrong.
Okay. Yeah.
Yeah. Don't take my word on that one, by the way. Thanks, Margaret. It's good to not see you, if you see what I mean, but I'm glad you could join us.
And there's a nice email to say, a nice message. John Merrill's found 12 more binary stars with Gaia, and been discussing it with some of us beforehand. So that's really good. This is a really great time for open data.
It's wonderful, isn't it? Yeah.
Anyway, it's now 15:23, so I'm 3 minutes past. We're supposed to be kicking off. So I should hand over to our Vice President, Robin, who is going to tell us about what's up.
Yes, okay, make sure I share the right screen. There we go. And I've just got to go back on my control. Yes, there we go. So this is what's up in the next, 3 months, November 2020 to March 2021, and let me just go past that screen, and here we are. This is the sky that you would see, not actually tonight, but very close to what you would see tonight, looking south. And I've chosen the date 14th of November for a good reason, and that is the start of National Astronomy Week. Now, I was asked this morning at the council meeting, when is this taking place? Well, I'm going to mention it now. It's the 14th of November to the 22nd. And of those of you who can subtract 14, 20 from 22, you'll realize it's an 8-day week, but that covers both weekends. Now, a bit of background. We originally planned National Astronomy Week, and the SBA is a sponsor of NAW, I should say, and we have been for many years. The National Astronomy Weeks occur when there is something of interest to show to the general public, and the idea is to get everybody, all the science centres and the amateur astronomers around the country, all pulling together at the same time to talk about something of real interest in the sky. And this year, of course, it's going to be the appearance of Mars, the close approach of Mars. We originally planned this about 2 years ago, at a time when nobody had ever heard the word COVID. And of course, we chose a week where the planet would be high in the sky in the early evening. And that's why we didn't do it at the time of opposition, which was about a month ago, when the planet was at its closest. But when it's at its closest at opposition, it's also at its largest, but about 1 in the morning, and it's at its highest at 1 in the morning. Whereas this time of year, not only is the planet a little bit is high up earlier in the evening, but also we've gone past the end of BST, so the skies are darker early in the evening, and that means that our planning was that school children could get out and do the public observation sessions that have been a feature of National Astronomy Weeks for many years. But then, of course, COVID happened, and we wondered which we cancel. But then we realized that, well, we could still do something online, and that is what is going to happen. And so the plan is that National Astronomy Week will be there for looking at Mars, and people can do it from their back gardens. And if they've got binoculars or a telescope, they can look for themselves. But we'll also be giving the public a chance to share with astronomers the excitement of looking at the planet through their own telescopes, through the astronomers' telescopes, telescopes and taking them into their observatories. And there will be a wonderful program of events during National Astronomy Week. Back to the appearance of Mars, you can see there, I think you can see my cursor, Mars in the middle, square of Pegasus up here. Here is the constellation of Andromeda, those 3 stars. That one is shared with the square of Pegasus, of course. And even the Andromeda galaxy just there you can possibly see. And then you've got the constellation of Perseus, the Pleiades, Taurus, and you've got Mars, you've got the planet Uranus. I will be in the next few days putting a finder guide to how to find the planet Uranus. It's actually quite easy to spot if you start from Aries there and then the square of the head of Cetus, and you can find Uranus quite easily. And here's the constellation of Cetus down here. So that's the things to look out for there. Oh, we've also got Orion just coming in over the left-hand corner there. But National Astronomy Week itself is focusing on the planet Mars, and I just had to show this photograph. This was taken a couple of nights ago, as you can see on the top right, it says October the 27th. And you might think that was a Hubble Space Telescope picture, but it was actually taken by a British amateur, the well-known astrophotographer Damien Peach, whose name's down the bottom left. Now it says Chilescope, which means that he was using the 1 meter telescope in Chile, which is available for remote observing. So he didn't have to move from Sussex where he lives, and he took this absolutely superb photograph, which I think actually has higher resolution than any of the pictures of Mars taken by the Hubble Space Telescope. You can see the Valles Marineris there, for example, in that gap there. I've never seen the Valles Marineris in such detail from an Earth-based telescope, and actually one on the surface of the Earth. Why should Damien be able to get better pictures than the HST? And I'm sure it is. I have not seen a sharper picture from the HST of Mars. And I checked the resolution of the Hubble Space Telescope, and it is actually not all that great. It's surprising. It has its most sensitive, most highest resolution camera, called the HRC, high resolution camera, actually has a field of view of about 29 arc seconds, and it has a resolution of only about 1400 pixels. So actually about the same as an amateur camera. And Damien, of course, uses the technique of what's called lucky imaging, which is to take a video sequence. And if the seeing is good, then he's actually getting, well, with a 1 meter telescope, just as good results as the HST. So that is a fantastic result. And you can see also Olympus Mons down here, an absolutely wealth of detail. The South Polar Cap with a rift on it. This is with South at the top, of course. The South Polar Cap never quite disappears. And clouds around here and on the morning terminator. You can see that it's past opposition because there's a bit of shadow on the left-hand side there. So on the right-hand side there, so on the as it's moving away from Earth. Mars at this time is moving away, pardon me, from Earth quite quickly, but it will be around for a long time, well into next year, and even in the middle of next year, it will still be in the evening sky, but very small. So get to it as soon as you can if you haven't observed it already, and certainly during National Astronomy Week. Now, here's the website for National Astronomy Week. I'll give you the website in a minute. And we have had a problem. We were hoping we had a map, which we spent a lot of time trying to get together before we knew that there would be no live events taking place. But now we have a full sequence of events taking place every night of the week, and even during the day in some occasions. And this is the website. If you click on NAW events, I can't scroll, this is just a screen grab, but you can see that on the first day, the Saturday, the 14th of November, Chris Lintop will be there. Jane Greaves, whose name you will know for the discovery of phosphine in the clouds of Venus. And on the Sunday, Mars Rocks, that's about geology of Mars, and Anna Halston and Suzanne Schwenzer, who spoke at the recent SPA meeting on Martian geology from the Curiosity. And in the evenings, there will be live streaming of the planet from whatever observatory can get to it. And we had a practice yesterday, and here's a lovely treat. This is actually a live stream that was taken, actually not from this country. It was cloudy more or less over all this country, but this was taken from an observatory in Cyprus, a chap called Agapios Elias, and he had his telescope going, and that's the view that he saw last night, and we live streamed, and that's what we're hoping to show. And you will actually be able to share in the live stream with him and with the others who are doing the observing, and they will explain how they take the images, how they then process that jiggly image, which is actually quite good seeing, and into a superb photograph, not quite as good as the one that Damien showed, but nevertheless showing a lot of detail. And so there's the website for National Astronomy Week, astronomyweek.org.uk, easy to remember. And we've got something you can help out with. There is a YouTube channel for National Astronomy Week, and we've put up a rather nice video which was narrated by Heather Cooper. Now, Heather, as you know, sadly died back in February, but she, back in 2003, narrated a video which was then a PowerPoint presentation about Mars, and we have brought that up to date and done it again as a video presentation for NAW this time. And interestingly, she referred in her commentary back in 2003 that a sample return mission from Mars was hoped for by the end of the decade. I didn't actually have to change that, because we're still hoping for the sample return mission by the end of the decade. It's the sample return from the mission that's going to Mars at the moment is due for 2031. So if you could go to the video, and I've shortened the URL there because YouTube videos are terrible, as you know. Their file names, tinyurl.com/NatAstroWeek. Now, if people can go to that, view the video. You don't have to view the video if you don't want to, but if you could subscribe to the channel, because we've only got about 61 subscribers to it at the moment. And if you could just subscribe, it's free. You don't have to pay anything. You don't have to give your name and address or anything. And then we will boost the number of subscribers to that channel. And once we do that, we can get a sensible URL for National Astronomy Week channel, just as we have in the case of the SBA, where it's youtube.com/popastro, and we will be able to get a sensible URL for National Astronomy Week. Going back to the sky, another event that's happening later on in this year, and I've mentioned this before. As you can see, the date this is taken from Stellarium, 12th of December, the 21st of December, and this is the sky just after sunset, about an hour or so after sunset. And those two images there combined, Jupiter and Saturn, will be extremely close together. They haven't been as close together visible from the UK and at a sensible time for something like 400 years, since the time of Galileo. So that is something to observe if it is clear in the early evening of the 21st of December. And of course, a day or two on either side, they will be pretty close. And here's a grab from Stellarium. You can see that the two planets really close together. They will be visible in quite a high power field of view of just an ordinary telescope. So that's something well worth looking out for. And I've never seen it before. The last two occasions, one in this happens about every 20 years, and the last one was unobservable because it was too close to the sun. The one before that, was very early morning, again almost unobservable. And the one before that, 1961, I don't think I've not heard of anybody ever observing that. So I was certainly too young to take an interest and have a telescope suitable at the time. So that's something to look out for on the 21st of December. And just the usual thing that we talk about at this time of year, meteor showers. And we have the Leonids coming up on the 17th of November. A fairly favorable appearance, because the ZHR, that's the hourly rate that you would get under ideal circumstances, is 10 to 15. So you might be lucky to see, say, 5 or 6 an hour, nothing spectacular. The radiant doesn't rise until 10:30 at night, so no point in observing, hoping to see large numbers before that time. But there will be no significant moon. It's virtually a new moon. So that's something to look out for during National Astronomy Week. And then we have the Geminids on the 11th of December, and a much more prolific shower, visible all night. So the radiant is up by the time it gets dark. And again, no moon, so well worth looking out for. Hope for clear skies then, and those can be a very spectacular shower, so look out for those. And then we have the Quadrantids on the 3rd to 4th of December, January. That's the best night. The actual maximum takes place during the day on the 3rd, and so the early evening of the 3rd to the 4th is probably the best time to look, or you might look on the morning of the 3rd in the early morning. That's ZHR again of 120, so you could possibly see quite a good number. Excuse me, I'm going to have to. So that's again visible all night, but quite a bright moon. So that's not so spectacular. So at that point, I'm going to stop my screen share and hand back to Stephen.
Thank you very much. And you made me Google the HST instrument capabilities with Wide Field Planetary Camera 3 and ACS and stuff. And it's a complicated thing, because the HST really only has a small field of view. It's arc-minute scale, as you rightly say. So you've got to somehow capture all of Mars by dithering around and getting it all. As to what the exact resolution is, compared to the, as physical kilometer resolution on the planet, I don't know how they compare. It's hard to beat HST in terms of arc seconds, but how it compares physically, I have genuinely no idea.
Yes, I looked at the most recent pictures from HST of Mars, and they haven't taken any this year that I've seen. There was one in 2018, which was actually a similar resolution to the one that Damien took. So it's certainly impressive, the photograph that he took, and certainly equal of HST.
Well, I would encourage people to have a rummage of the images. We're in a good time of open science. HST have released their data as, in fact, you can go into the ESA sky and look at the actual astronomical FITS images if you really want to. But there's good PNGs and TIFFs around as well. It is very, very impressive, and the HST is well sub-arc second resolution. It's amazing things you can do from space astronomy. But yeah, that's a really very impressive image from a ground-based image, a beautiful one. So fantastic. Any questions for Robin?
I don't believe there are any on YouTube. I'll have a look, but
It was that.
No, nothing on YouTube yet, so no questions by the look of it.
So it's been pointed out that today is Dark Matter Day. I didn't know that. Ooh. I work on gravitational lensing. Oops. Wow. So yes, if you search on search today for Dark Matter Day, you'll find a lot of talks on and stuff online. And I've put an animation in the chat, which you can have a look at afterwards, which I hope you like.
And I see that Margaret Penston tells us to look out for the Star of Bethlehem on the 21st of December, which is a good point, because the Star of Bethlehem, one of the explanations was that it was a conjunction of two bright planets. So maybe we will get a few people claiming that they had seen the Star of Bethlehem just before Christmas. The only thing is that Saturn visually is a lot less bright than Jupiter, so the combined appearance of them will not be the same as, say, Jupiter and Venus, where that will be a really bright object. But Saturn will be quite a lot fainter visually than Jupiter, so maybe not quite as spectacular as the Jupiter and Venus.
Yeah. If there are no other questions, I suggest we go on to Bob. who will talk to us about meteorites.
Mm-hmm. In fact, a very special meteorite. The title of my talk, which will appear eventually, is the Cape York meteorite. Some people have never heard of this. It is, in fact, the biggest meteorite in captivity in a museum anywhere in the world. There are larger meteorites lying around in Namibia and Argentina that are bigger, but this is the one that you can, well, not at the moment, but people can go and see in a museum. But there's a lot more to the Cape York meteorite than just being a meteorite. First of all, let's talk a little bit about meteorites in general. I'm going to show you 4 other meteorites in captivity from my little cabinet in the next room. And most meteorites, in fact, are chondrites. And to get an idea of the scale of this one, if I just hold it up next to my head, you can see it's not a very large sample. There are much bigger chondrites in the world than this, but about 90% of all meteorites found are chondritic meteorites. Here's one, put it up there, you can see it. And the brownish effect is actually Saharan sand. You don't clean these things because that's all part of their history. And this has been lying in the Sahara for 5,000 years since the mini asteroid that created it blew up over that desert and dropped hundreds and hundreds of pieces all over Algeria, Morocco, and Libya. These are very easy to get. If you go to Space Rocks, for example, the website, whatever, you can find them. Most of the rest of the meteorites are ions. On this little magnet here, you can see dangling is a very small sample of the Campo del Cielo meteorite from Argentina. Ions tend to be much rarer and therefore a little bit more expensive. And here's, held up by the magnet, here's that object. It's a sort of crystal, if you like, a giant set of iron crystals. And on many of these, if you cut them, you can see the interesting crisscross Widmanstätten patterns inside. Why the difference? Well, if you like, here's a piece of the crust of an ancient asteroid or planetesimal that was smashed up at the beginning of the solar system when everything was orbiting in chaos. Here's a piece of the interior, because like the Earth, many of these largish objects had differentiation of materials where the heavy stuff, the iron, sank to the center, and the rocky stuff, the silicate material, stayed on the outside. Now that's why meteorites are like this. The only meteorite I've ever actually found is this one. This is together. Oh, thank you for enlarging my picture, whoever did that. This is from the side of a road near the Rochechouart crater in France. Rochechouart is a fantastic crater. It's about 30 kilometers in diameter. The town of Rochechouart sits inside it. We didn't stay in the Hôtel de la Météorite because it didn't look quite as attractive as the one next door. And so we stayed there instead. But while driving in the vicinity, we stopped in a lay-by for our sandwiches, my wife and I saw this lump of old concrete, yeah, amongst the crisp packets and the Coke cans, litter at the side of the road, and I picked it up. When I was a young man, a long time ago, my Uncle John invited me to work on his building site during my university holiday. And one of my jobs on the building site was to beckon the concrete mixer lorry, you know, the big round and round thing, onto the site, bits falling all over the place. And my job was also to pick up all the rubbish afterwards and dispose of it. That's not a piece of concrete. Concrete just doesn't look like that. You've got a bit of dirt here from that French hillside by the lay-by, and you've got all sorts of different colored material. You've got lots of very interesting sort of orangey bits. Could be rust. And I took it home and I took it to my monumental mason, the old gravestone maker here in Dorset, and he polished it for me. And you might be able to see there little tiny black bits, orangey stripes, and all sorts of interesting things. That's a breccia. That's a thing made of infalling material and earth material mixed up. And from the Ries crater in Bavaria, one of the best known European craters, we have this piece here. Again, it's been polished, and that's a breccia. You can see it's just a pudding of hundreds and hundreds of tiny pieces of material. The black stuff is glass made by the impact. The grey and black pieces, parts, I think, of the original meteorite, and grey stuff, the matrix, is just a huge mixture of everything. And it's all gone up in a gigantic cloud and fallen back down again. And you can find this stuff around that area if you're very lucky. You can go to the incredible Eugene Schumacher Museum, named after that great geologist who investigated so many craters, in Nördlingen, which is inside the Ries crater in Bavaria, the town of Nördlingen, fantastic medieval city. And you can see samples of this, much bigger than this, in that museum. So there's a few meteorites. Now, if I can share my screen, which I hope works, here we go. Right, let's enlarge that. It doesn't look like a meteorite to me. What is that? Well, of course, if you know me, you'd expect me to crowbar in something about light pollution. And here, hang on, let's get back to the beginning. This is, if you're interested in doing something about light pollution, I'm sad to say that many amateur astronomers don't. But if you'd like to really have a go at the problem and talk to the right people and join the new all-party parliamentary group of MPs, collaborate with them, send them your opinions. In that book, with a pen there for scale, you'll find these chapters: The Disappearing Universe, Environmental Aspects of Light Pollution, Lighting and Crime, Light Pollution and Human Health, LED lighting, Blessing or Curse. It's mostly a curse, actually. How do you take action about light nuisance? What are the principles of good lighting, and what should you be telling your local council to put in, because quite often they haven't a clue what they're putting in? How to complain about poor quality lighting? Well, I think you've got the idea. That's a darn good book, very recently done, about light pollution. Go to the Commission for Dark Skies website. You can see the words there on the book, I hope. And just search Commission for Dark Skies. Go to the queries contact form and ask me if you'd like a copy of that. It's not expensive. Let's talk about meteorites. There's another chondrite from the Sahara. Again, you can see the sand there sort of infused into the exterior. But these impacts create more than just sandy surfaces. They create glass. This is from Libya, the second one, if you can see my cursor. Libyan desert glass occurs in sheets and fragments around the Libyan desert. And there are the famous moldavites, of course, a very similar kind of material found in the Czech Republic. And that has been thrown from the Ries crater in Bavaria, hundreds of kilometers onto these sites to the south in the Czech Republic. It wasn't called the Czech Republic then, of course, 14 million years ago, but that's where you can find them today. Beware of fake meteorites, or meteorons, as they are often called in the meteoritic community, because they're not the correct stuff. You can make things like this. Please don't. This is part of the Arizona meteorite. Andy showed us the Barringer crater, which was mined by that rather unfortunate person, Mr. Barringer, who didn't really find much iron down there and ran out of money. But you can see there on the back of the thing, there are these, I think they're called Neumann lines in this case, which represent the shock of an impact, possibly in space before the thing even got here. Not long after I was born, 1947, this one fell in near Vladivostok in the far eastern province of Russia. This is the Sikhote-Alin meteorite here, bottom left. And this is contorted and twisted, an airburst, which flew through the air, and millions of bits of iron, most of them fairly small, about the size of your thumb or something. And a lot of them were embedded in trees. And to this day, meteorite hunters go climbing up trees in the far east of Russia, not to amuse their friends, but to discover little bits of the Sikhote-Alin meteorite. Tektites, very commonly found in Vietnam, China, Australia, and these are glass. They don't look like glass, but glass isn't always transparent, of course. And again, created by the fall of a meteorite. And this thing certainly isn't a meteorite, but it's a shatter cone from the Reese crater in Bavaria. And you can see these radial lines here, which are simply a shock effect of something hitting the surface above and deforming the bedrock below. So here's a moldavite, green glass, and Darwin glass from Tasmania. And that's the breccia that you saw earlier from the Reese crater. So this gives you an idea of the real variety of meteorites and impactites that you can find. That's the Rosh Hashanah crater. Doesn't look much like a crater, of course, because the event happened 202 million years ago. May well have been part of a quintuple meteoritic strike, which formed the Manicouagan crater in Quebec, in Canada, a couple of craters in the USA, one in the Ukraine. This is Rosh Hashanah. The chateau is partly built of meteoritic material. A lot of those stones there are breccia from the local quarries. This is the Roman baths at Chassenon near Rosh Hashanah. All these stones are meteoritic impactite material. The Romans didn't know what they were handling when they built it. This is the church door in Rosh Hashanah. And again, a lot of this material, the dark stuff, is from the impact more than 200 million years ago. And there's the Hôtel de la Météorite, and there's a Pharmacie de la Météorite, and all sorts of other references. Okay. There are, of course, UK meteorites. They tend not to be as large as some of our European counterparts, but Barwell meteorite. My daughter lives quite near Barwell, and as I drive through it, not nowadays, on the way to see her, I have a little glance. You know, you shouldn't really do this while you're driving, but I never see anything lying about. I think they've all been picked up by now because it fell, as you can see, on Christmas Eve, 1965. The Glatton meteorite from Cambridgeshire, 1991. In the 2000s, this is the little Northallerton meteorite. And not a lot of people have heard of this one. This is the Middlesbrough meteorite weighing 1.5 kilograms, as you can see, from the 19th century, actually seen to fall by railway workers who were digging out a cutting, and it fell on the other side as they were working. The grandson of William Herschel, Alexander Herschel, examined this when it was reported and confirmed that it was of meteoritic origin. Have we got any craters in the UK? Yes, there's the Silverpit crater. There it is. You'll have a hard job visiting that one. You need your scuba gear because it's under the North Sea, 20 kilometers down. Okay. And here's the Lairg crater up here in northwest Scotland. Some of the outfall from it is on the beaches near Stour Bay, just north of Allapool. And there's a piece of that. And this is the geology of the Lairg crater. Again, there's not much to see, of course, after 1.2 billion years, but it is an extremely large thing. When that happened, of course, Scotland was joined to Canada. The Atlantic didn't exist. And the largest meteorite that you can actually go and see, I think, on the planet is the 60-ton Hoba West meteorite in Namibia. This was just over 100 years ago. A farmer called Jacobus Britz was ploughing with oxen and came across something really hard in the soil, assuming it was a piece of discarded farm machinery or something. He dug around and dug and dug and dug, and days later he'd uncovered this massive piece of iron. And not all that long ago, it was protected as a tourist attraction. Before that, people had come to chip bits off it, and so it's not quite as big as it was. Let's talk about the Cape York meteorite. That's what I'm supposed to be talking about. And here's a piece of it in Copenhagen. This is the Copenhagen Geological Museum. And there's a piece outside, there's a piece inside. And this is about the size of a large fridge, I suppose you'd say. And it's on a plinth just outside the museum. I don't think they're worried about anybody carrying it away. because that piece weighs several tons. And there it is at night on its little plinth. It's called Agpalalik. All the parts of this Cape York meteorite have names, and in the Inuit language, they all have their meanings. There's Cape York. It's on the western side of Greenland, as you can see, and it's estimated that the meteorite fell about 9,000 years ago just here. The first mentions of it to Western Europe were made by Captain John Ross, 1818. You may have heard of the Ross expedition. He may well have been looking for the Northwest Passage and other things in that region, but he met the indigenous people at Melville Bay, and they didn't have anything in common language-wise, but somehow they managed to indicate that the iron, which they had at the tips of their hunting spears, were from a certain direction, and he was unable to go in that direction because of the weather. But he realized that somewhere over there, there was a considerable source of iron, and brought back several of the Inuit tools with their iron blades to show. Here's one. This is a walrus bone with a meteoritic iron tip. I don't know if Ross knew about the possibility of meteorites being sources of iron, but it was their only source of iron, of course, living on this icy waste. And they would hammer off chips and flakes and melt them into spearheads. This is the tent, the Anigito. Any Inuit people listening, please excuse my pronunciation. This is the largest piece of the Cape York meteorite discovered, and it's the one that is most prominently displayed in the New York Museum of Geology. So 8, it may be 9 pieces of that particular meteorite have been found. And here's one of the American expedition, which we'll talk about, standing next to the thing to give you some sense of scale. The pieces are all quite weighty. You'll see that the tent, the one that we just saw, weighs 31 tons. And it was discovered, no, hang on. I mustn't say it was discovered in 1894. I think the Inuit people discovered it long before Europeans and Americans went there to see it too. So it was discovered, heaven knows when, by the Inuit people, and the first time somebody from the Western world actually saw the thing was in 1894. There's another one called the Man, 20 tons, as you can see, and that's quite a hefty thing. Savick 1 and 2, they are respectively 3.5 and 3.5 tons and 7.8 kilograms. These are the smaller pieces. Okay, there's the woman meteorite and the dog meteorite. They don't look much like a woman and a dog, and the man doesn't look much like a man, really, but that's what they called them. This one's named after the place where it was found, the Tonuaput, that's 250 kilograms, so we're getting a bit smaller here. It has the honor of being the first meteorite ever discovered in the sea, because it's covered by high tides. So there it is. There's the tent. Small child for scale here. Okay. And discovered by Peary, the American explorer, in 1894, discovered a long time before that by the locals. Point of interest, I suppose, in those days they paid $40,000 for the meteorite. Here it is again. Here's the dog. I can just about see a dog there. I'm afraid I can't see a woman there. It's a stretch of the imagination, I think. These are the other 2 large pieces that are in that New York Geological Museum. And from the various pieces, allowing for ablation on the way through the atmosphere and people chipping bits off, etc., it was estimated at the time that the thing probably weighed about 200 tons when it came through the atmosphere. flicking back and forth. This is the Woman meteorite. There it is. And there it is in situ among the rocks and ice of Greenland before it was lifted. And here's the person who lifted it, not all on his own, of course. This is Robert Peary, Commander Peary, well known at the time, American explorer, navigator, and most of the time he navigated aboard the ship Hope here. That's him in not traditional American dress. I think he's probably going somewhere very cold. And in 1894, he landed on the coast of Greenland and bribed a local, it is said with a rifle, to take him to the location of the meteorite. And having sized them up for possible removal, he decided to take 3 pieces, the ones you've seen, to the USA. Another person who transported pieces of this away, this is a Danish explorer, Knud Rasmussen of the 1920s, and he took the last 2 remaining pieces, not the last remaining, the last 2 remaining pieces, which sadly, and although these people probably realized this at the time, but they did it anyway, they deprived the locals of any source of iron, and they were no longer able to use the meteoritic material for their spearheads, probably affected their hunting. Somebody found a much later piece, you might have noticed it in the list, in 1963, and that's also in this museum somewhere too. So the story of the tent meteorite, the big one, the 30-ton one, first of all, Peary exhibited it on board his ship in the Brooklyn Naval Yard. People came to see it, they paid money to see it, and later it was brought down onto the dockside, and for some long time, that was where it was shown, as I said earlier, with very little likelihood of anyone trying to steal it. It did weigh rather a lot. Peary must have got together a huge amount of engineering equipment and laborers to move these things, but he managed to get them to New York. Another thing he brought, of course, was 6 of the Inuit people. There are some of them there. You can see this little chap here. There he is. That's Minik, age 7 at the time that the photo was taken. And as often happens when indigenous people meet people from other parts of the world they've never met before, 4 of them died very shortly afterwards of tuberculosis. One of the dead people was Kizik, the father of the young lad, and of course they weren't quite sure what to do with him, so he was adopted by the curator of the Natural History Museum in New York, William Wallace. A very sad tale, because Peary also actually dug up remains of Inuit people from their graves and brought back the skeletons for exhibition, to quite horrifying perhaps to modern ears. Minik, that little lad, discovered 10 years after his father's funeral that he hadn't actually seen his father been buried at all. They didn't bury Kizik, the father. They kept him for later dissection and exhibition of the skeleton in the Natural History Museum. And what the boys saw was a parcel of stones and bits of wood wrapped in a sheet being buried. It's a very sad tale. The museum refused to return the remains, and Minik, the boy, now grown up, went back to Greenland. And in 1916, I can't find out the reason, he returned to the USA, only to die of the Spanish flu in 1918, which did for millions of people in the Western world. Finally, in 1993, all, in a more enlightened time, all the Inuit remains that they had in New York were taken back to Greenland. And here's the marker on the grave with a plaque, which was laid by the Queen of Denmark, administering Greenland. And it says on it, if I can read it, Nunamingnut Utekuyut, which means they have come home. And that's the end of a tale which involves a lot of exploration, a massive amount of engineering, a wonderful exhibit for the New York museums, and also a very sad tale of what can happen to people if they're interfered with by others who don't really know what they're doing. So that's the tale of the Cape York meteorite. Thanks very much for listening to me. I hope there's some time for questions if you have any. And one of the wonderful things about meteorites is that, that they all have their own individual stories. You can find on them residues of where they've been, sand, soil. You can find shock marks where they've fallen, and all the surrounding rocks have all these wonderful indications of the impact too. Go and visit these craters. There are craters not all that far from Britain. There are some in Estonia that you can visit, fairly small ones. There's those two wonderful craters in France and Germany. And when travel becomes a possibility again in this rather troubled world of ours at the moment, go to Rochechouart, stay in those hotels, stay in the Meteorite Hotel if you like it, and drive around the crater. It's a wonderful thing. Visit that Roman bathhouse. See the fantastic work that was put into that. You may have been to the Roman bath in Bath. This one's totally different, completely different, wonderful thing. And go to the Ries crater in Bavaria. Go to Nördlingen. Look at its fantastic medieval city wall, one of the 3 medieval city walls that are still intact in Europe. Go to the tremendous buildings in the town, go to the Meteoritic Museum named after Eugene Schumacher. And there is also one in Rochechouart too, where you can see all the different types of rock indications of the meteoritic strike about 200 million years ago. That's about all I've got to say on that. I'll stop sharing and hand you back to Robin or Stephen. Thank you.
Thank you very, very much. That was really very interesting. And for the 3rd time today, we'll have a huge imaginary round of applause. So there have been a few comments on questions. There was a point. Someone's pointed out. John Murrell has pointed out Tim Gregory's talk at the last SPA meeting had lots of stuff on meteorites. His book covers a meteorite that caused the crater at Nördlingen.
Yeah,
Bob talked about.
Ries crater, yeah.
Yeah, and a lot of buildings are built from the shocked rock from the impact. Yeah. And apparently, the impact formed microscopic diamonds.
Yeah.
Through a microscope, which is
you can see them in this.
Really?
Well, you can't see them because they're absolutely sub-microscopic. But if you look at that under a very powerful magnifying glass or under a microscope, you can see tiny little glittering points, and they're diamonds created by the impact.
Wow. It's just glorious, actually. Just glorious.
This is what I'm saying. Every meteorite has a story. You know, it's wonderful.
Yeah, and thank you also for pointing out the also some fairly grim stories of human exploitation behind them. It's we like to think of science as having just a pristine history of scientific abstract inquiry, and it really doesn't. It's a human activity, and as such, there's lots of lovely and glorious things, but there's lots of darkness as well. So it's important that we don't forget that. So that was really, really interesting and important. There was a question. Catherine on YouTube was posted for Bob that she's heard that a recent experiment showed that most of the light pollution is not caused by street lighting, but is caused by advertisements and lit buildings and floodlights and sports stadiums.
Yeah, this is in fact nothing new.
Yeah.
For years and years, it's been obvious to anyone who just is in or near a city that most of the light that's wasted is not from road lights, because mainly thanks to the efforts of the CPRE and the Commission for Dark Skies and all sorts of other people, if you look at nearly any road light nowadays, it shines straight downwards. Most of the LEDs are far too bright, which means that there's a lot of upward light reflected, which is bad. And the people who put these things in really ought to think about these things. You don't need a floodlight to light a road. You need a nice subtle light so everybody can see what they're doing. And sports lights, for example, in Bristol, the cricket ground there is a massive source of light pollution. Why? They're not playing cricket in the sky, you know. And, and this recent experiment was in Tucson, Arizona. They looked at satellite images of Tucson, Arizona with variations in the lighting, and they assessed that most of the light did not come from the road lights. But of course, road lights will cause light pollution if they're too bright. Doesn't matter if they're directed downwards or not. But sports lighting is completely unregulated in this country. And this is one of the things that the MPs, this group of MPs, the all-party group for dark skies, is addressing. You know, all these non-road light sources, people's so-called security lights. They don't give you any security because they don't defeat crime. But why are nearly all lights sold in retailers, I won't mention names, in the big retailers where you'd go to buy an exterior light? Why do most of them shine upwards?
Yeah.
Because they're made in places in the Far East, for example, where there are no design standards. And you buy one for $5.99 and it destroys the night sky, dazzles the neighbors, and doesn't stop crime because, of course, it's so bright that you can't see anything what's going on. It's a good light to sort your tools out if you're a burglar.
Yeah, and it's not just humans that suffer, it's also wildlife as well. And
well, biodiversity crash is partly due to light in rural areas. Tell me a totally dark place in England. There isn't one. And if you're a glowworm, that's bad news. You can always see some remnant of city lights on the horizon anywhere in this country. Scotland and Wales fare a little better, not so many really big towns there, but you know, this is the tragedy of light pollution. It's so unnecessary. Anyone can point a light where it's needed, not too bright. Rocket science, it is not. I'll stop ranting now. And
no, I'm with you on this. I was once on a holiday where I think it was a new moon, and in the middle of the night there was a power cut, and I woke up, and we had the curtains closed and stuff, and I thought I'd gone blind. I did not realize that the world could be as dark as that. And
most people have never seen true darkness. And it's a massive tragedy that 90% of people in the developed world have never seen the Milky Way, their home in space.
Yeah,
you may have heard about the Los Angeles power cut some years ago, and people were phoning the police and saying, what the hell are all these lights up there in the sky? Oh, they're called stars. It's the Milky Way.
Really?
Yeah,
that's astonishing. Wow,
I'm making this up.
Wow.
When I was a little boy in East London, these street lights used to go off not long after World War II. The Second World War broke the economy of this country, and the street lights went off at 10 p.m. and we used to stay up late and just watch the stars. It was fantastic. No child in London sees any stars now. You might just see the moon, a couple of planets, but isn't that awful? I mean, if all the lighting in cities were correctly done, you'd see constellations from Trafalgar Square.
And that would be wonderful.
But there's no regulation, you see, there's no laws. It's the only part of our environment with no protection in law.
Indeed. I noticed Chris Lintott has just published a paper with another Lintott. I don't know if this other Lintott is related, about the effects of light pollution on biodiversity. So
it's causing massive dieback of all sorts of species. Bats, for example, you know, many bats won't fly anywhere near a light. The horseshoe bats, they don't like it. And if you put up a light near a bat roost, they don't emerge, they won't come out, and they'll starve rather than come out. Any more questions?
Yes. There was a comment on the chat that there's a from John Morrell. There's a piece of the Cape York meteorite around 10 inches long in the Natural History Museum in London.
I didn't know that.
Yeah, but not clear if it's
I'll
on
see
public.
that one day.
Yeah, it might not be on public view though. That's the thing, because they've got a big reserve collection.
Oh, I know,
They
yeah.
can't show everything.
Yeah.
Yeah. The NHM it's just a glorious place. It's really, one day when we can go places again, it's absolutely worth a visit, I would say. Any other questions? I don't, and I suspect people are just a little bit tired now, because it's been a long day of lots of really, really very interesting talks. So I think 4:15, I think we should call it a day. And thank you so much for everybody for connecting. It was really, really very interesting. So many things. And our next meeting, I think, Robin, is in January. Is that right?
That's the next scheduled meeting. Yes, at the end of January. We reserve the right to hold another one if something happens in between now and then. So keep an eye on the website, and we will let everybody know if we have planned one. But that's the next definite one. Dr. Andy Newsam, who is also a cosmologist like you, and Stephen Feeney. Feeney, who's going to be talking about the crisis in cosmology caused by the Hubble constant and the different versions thereof. So a bit of cosmology there.
Yeah, and a really, really hot topic in cosmology. It's causing a lot of people to scratch their heads. It's probably the most interesting crisis well, for me, in extragalactic astronomy at the moment. It's fascinating. But there are so many wonderful open questions at the moment. Everyone has their particular preference. So this is mine. Fabulous. And of course, there's the SPA Facebook Live events that Vicky Duncalf runs.
Indeed. And one thing I should mention is that I've been asked to push the merchandise, which of course we have now more items on our website, and Vicky is very good at promoting those. I was hoping to get a little ad from her to play today about the new jewelry that's on the website and various other things. We've also got some Christmas cards. They'll be on the website hopefully tomorrow. Just a small, very exclusive run of Christmas cards, $4.99 for a pack of 10. And those will be on the website tomorrow. They show a lovely picture. In fact, I don't think I can show them to you, but there we are. That's what we'll be doing. Got Aurora on there, so that will be. It's got season's greetings on the inside. So we hope to get it on the website tomorrow. So do look at the website for lots of wonderful Christmas gifts.
Lovely. And with that, thank you very much, everybody, for attending. Stay safe, and
Thank you very much.
And don't forget these glorious books by Bob and by Andy as well. And Christmas is coming.
It is.
So take care, everybody, and stay safe.
Yeah.
Bye, everybody.
Bye.
Bye.